So, you ever stop and think about how a pilot knows exactly where their airplane is, floating somewhere over the middle of the ocean? I mean, there are no roads, no landmarks, literally nothing but water in every direction. Or think about a surgeon operating a robotic arm, guiding it to the exact millimeter inside a human body. Or how astronomers point a telescope at a galaxy billions of light years away and know for a fact they're looking at the exact right patch of sky. Well, the answer to every single one of these questions actually comes down to one deceptively simple mathematical tool.
Welcome to this explainer. Today, our goal is to completely demystify the fundamental language that decodes physical reality. We're talking about the coordinate system. Without this concept, modern science, engineering, and honestly, civilization as we know it simply could not function. So we're going to break down how this invisible framework shapes absolutely everything around us.
Here's a quick roadmap of the chapters we're about to cover. First, we'll look at the fly on the grid, then embracing the curve. After that, we'll get into bending space and time, and finally, navigating the real world.
All right, Chapter 1, the fly and the grid, or the birth of Cartesian coordinates. Okay, let's dive right into this. Before we get into the heavy physics, I want you to picture something. Imagine waking up in a pitch-dark room. No windows, nothing. Suddenly, someone asks you, "Hey, where's the lamp?" You can't answer that question meaningfully unless you have some way of describing position relative to something else, right? You might say something like, "Well, it's 2 steps to my left and 1 step forward." And notice what you just did there. You used the 3 essential ingredients of any coordinate system. You picked an origin, your own body, you chose reference axes, left and forward, and you set a scale, steps. It's an incredibly simple invention, yet it gives us the power to locate literally anything in the universe using nothing but numbers.
You know, for a huge chunk of human history, location was purely qualitative. The ancient Egyptians used ropes and knots to measure land. But in 1637, everything changed. The legend goes that the French philosopher René Descartes was just lying in bed, watching a fly buzzing around on his ceiling, and it hit him. He realized he could pinpoint that fly's exact location with just 2 numbers, its distance from 2 adjacent walls. Boom. That birthed Cartesian coordinates, which was this monumental leap that finally fused geometry and algebra together. And that initial spark, it ignited a mathematical revolution. It took us from Descartes to Lagrange's generalized coordinates in 1788, to Einstein's 4-dimensional spacetime in 1905, all the way to the highly abstract coordinates powering quantum computing today in 2026.
Which brings us to Chapter 2, embracing the curve. Because sometimes straight lines just fail.
As beautiful as Descartes' flat grid is, it sometimes completely clashes with the reality of the physical world. So the crucial point here is that physicists do not just blindly stick to straight grids. Instead, they follow this golden rule. Choose the coordinate system that matches the symmetry of the problem. It's not that Cartesian coordinates are mathematically wrong, it's just that some coordinate systems make certain calculations extraordinarily difficult, while a cleverer choice makes that exact same calculation almost trivial. You always want to match your math to the actual shape of your physical problem.
Let me give you a concrete example to put that into perspective. Imagine you're calculating the gravitational pull of the Earth. Now, the Earth is a sphere. If you try to force a boxy 3D Cartesian grid onto it, the mathematical expression for gravity becomes this clunky, tangled mess of x, y, and z variables. It's a nightmare. But if you strip out that raw algebra and switch over to spherical coordinates, the exact same physical problem becomes beautifully elegant. Suddenly, the gravitational field depends on just one easy coordinate, the radius, or simply the distance from the center. Choosing the right tool totally saves the day.
So, this basically forms a physicist's ultimate toolbox. If we're looking at 2D circular symmetry, like planetary orbits for example, polar coordinates are our go-to. If we stretch that out into a 3D cylinder, say water flowing through a straight pipe, we use cylindrical coordinates. And for perfect 3D spherical symmetry, like hunting for an electron hiding inside a hydrogen atom, spherical coordinates take over. Think about it. Without them, our entire understanding of atomic structure and the periodic table would have been vastly delayed. Why? Simply because the math would have been way too nightmarish to solve.
Now hold on, there is a really critical distinction we need to make here. A lot of people tend to confuse a coordinate system with a reference frame. They are deeply related for sure, but they are absolutely not the same thing. The coordinate system is just the mathematical grid we draw, the labels basically. But the reference frame, that's the actual physical perspective or state of motion you are standing in while you make your observations. You can use the exact same grid labels whether you're standing perfectly still on the ground or riding on a high-speed train.
This distinction is incredibly important when we talk about rotating reference frames. Picture yourself sitting on one of those spinning playground merry-go-rounds, and you roll a ball straight across it.
To you, on the ride, the ball seems to curve away as if by magic, but to a friend standing still on the playground, the ball is rolling in a perfectly straight line. You are just the one rotating underneath it. That apparent curving force is what we call a fictitious force. The Coriolis force and centrifugal force aren't genuine physical poles like gravity is. They're just artifacts of the fact that your reference frame is spinning. And because our own Earth is a spinning reference frame, that Coriolis force is exactly what makes massive hurricanes rotate counterclockwise in the northern hemisphere.
Moving on to Chapter 3, Bending Space and Time, Einstein's ultimate coordinate shift.
All right, we are taking the training wheels off now and escalating the stakes. We're stepping into the totally mind-bending reality of relativity. Back in 1905, Albert Einstein realized that the speed of light is the same for everyone, no matter how fast they're moving. This completely shattered classical physics. His former professor, Hermann Minkowski, delivered this famous quote in 1908, marking a profound conceptual shift. He said, "Henceforth, space by itself and time by itself were doomed to fade into mere shadows, and only a union of the two would preserve an independent physical reality. We could no longer treat 3D space and 1D time as separate things. They had to be woven together into a single, unified, four-dimensional fabric, space-time."
Because of relativity, if you travel near the speed of light, bizarre things start to happen. Clocks literally tick slower, that's time dilation. Rulers physically shrink, that's length contraction. So if observers can't even agree on basic distances or times, what is actually real? Well, the answer is the space-time interval. It's a highly specific mathematical combination of space and time measurements that remains absolutely identical for everyone. Despite all those crazy relativistic effects, this four-dimensional coordinate measurement acts as the ultimate unmoving anchor of our physical reality.
10 years after that, Einstein expanded this into general relativity, revealing that gravity itself isn't a pull at all. It's actually the physical warping and curving of this 4D space-time fabric by massive objects. This blew the doors wide open and led to the discovery of black holes and the dreaded event horizon, the absolute point of no return. Now, early physicists noticed that their math blew up to infinity right at this boundary. They honestly thought nature was physically breaking down. And this brilliantly illustrates exactly why your choice of coordinates matters. It turned out the physical space-time wasn't breaking down at all. The original coordinates they were using were just failing. By switching to a clever new grid called Kruskal-Sakaris coordinates, physicists proved that space is actually perfectly smooth as you fall across the horizon. The math broke, but reality didn't.
And now, Chapter 4, Navigating the Real World, the year 2026 and beyond. Let's bring all these abstract, lofty concepts back home, because we literally rely on this stuff every single day. Look at this number, 38 microseconds. That is exactly how much faster the atomic clocks on GPS satellites run compared to the clocks here on the ground, every single day. This happens due to the competing relativistic effects of their super high speed and the weaker gravity up there. If engineers didn't explicitly program the mathematical coordinate corrections for Einstein's relativity into your phone's GPS software, that tiny 38 microsecond difference would ruin your navigation by 10 kilometers a day. Seriously, without coordinate transformations, the modern world would literally get lost in a matter of hours. And coordinates are the absolute bedrock of today's cutting-edge discovery. When LIGO detects gravitational waves from colliding black holes, supercomputers use these dynamic, constantly shifting coordinates to track the wildly complex space-time curvature. The James Webb Space Telescope? It relies entirely on a rotating reference frame to maintain its super delicate balance at the L2 Lagrange point, hovering 1,000,000 miles from home. Even the qubits inside modern quantum computers don't exist in ordinary space. They're mapped in a wildly abstract multi-dimensional coordinate system known as Hilbert space.
Which brings us to the very edge of the unknown. As theoretical physicists today try to unify general relativity and quantum mechanics into a grand theory of quantum gravity, they are looking down at the Planck length. That's an inconceivably tiny distance scale. And at this ultimate fundamental level, we really have to ask, will the very concept of coordinate systems and space-time itself even survive? Are we going to have to abandon them entirely for an even deeper underlying mathematical structure? It's a thrilling question, and it proves that the humble coordinate system is still our best key to unlocking the true fabric of reality. Thanks so much for joining me on this explainer, and hey, keep questioning the grid around you.